Hello, my name is Harper Mangine, and this is Physics Lab 5, the Choose Your Own Adventure Lab, and I chose to do the falling Slinky. So, the purpose of this lab is to predict the motion of a fallen Slinky from the stretch position, specifically from the bottom of the Slinky, and we're trying to see whether or not the bottom moves as the top of the Slinky, the stretch Slinky, falls to hit it. Real life application, Newton's second law, the energy principle, practice using position and velocity update formulas. So preview of the results is as the top of the stretched slinky falls towards the bottom of the slinky, it kind of acts like a spring, but the bottom of the slinky stays stationary until the top is fully compressed, and then it falls as one unit to the ground. So key assumptions of background, major forces are the spring force and the gravitational force. Drag is calculated into it, and then the object is only moving in the y direction. And in this case, the negative y hat. So some important principles, as always, Newton's second law, momentum principle, the spring force equation, the kinetic energy equation, which is derived from the energy principle, and then the spring potential energy equation. Those were like the big three that I used during this lab and during my coding. So the procedure, define your variables in the system, import the Slinky video into Tracker, track the bottom of the Slinky's position from the center of mass frame by frame for 7 seconds with 520 frames. It was a lot. And then create a computational estimate of the Slinky's motion by coding my own GlowScript code. And then look at the graphs and draw some conclusions. So our initial conditions. So here's the observed model. As you can see, it's the bottom of the slinky doesn't move until the top of the slinky hits it, and that's where the graph breaks and heads at like a diagonal downwards. And that's once the spring, like the slinky as a spring, is fully compressed and starts moving as like one mass unit instead of as like a stretched spring. The computational model, it very much resembles the observed model in the graph. However, this one's a little bit more smooth just because it's consistently moving down by the same interval over and over and over again, which was a calculated number. And so here's the code for it. It's kind of blurry. It's okay. Possible sources for error. Uh, I mean, human error is always, or mathematical error. The graph on the real graph is obviously a little bit choppier just because I have to guesstimate where the center of mass is. But the computational model is a little bit too smooth to accurately represent actual spring motion because nothing's going to move directly in like a linear line just because of the other forces acting upon it, such as drag, such as like gravity, literally just movement because of its surroundings. Lab questions, yay. So why does this bottom of the slinky remain stationary? The forces in the y direction at the end cancel out. So although the gravitational force acts downward, the slinky acts as like a big spring and it counteracts the force with a tension force of equal and opposite magnitude. So while the top of the spring, the slinky is falling, the force is of the tension is equal and opposite, so the bottom stays still until it collapses altogether. What if we put a large weight at the end of the slinky? Would the bottom remain stationary? And it would depend. As long as we have a slinky that is long enough or has a large enough spring constant so that the tension is the gravitational force, that's when it would remain stationary. If the tension and the gravitational force canceled each other out like they do in this video, um, if not, the weight would pull the spring down as the top of the spring is moving, so it would kind of move in the stretch position towards the ground. If it were to remain stationary because the tension and the gravitational force were equivalent, the weight would remain stationary at the bottom, just like in the video, until the top of the spring reaches the body, and then it would probably just accelerate a little bit faster towards the ground just because there's more mass behind it once it starts moving as a unit. Thank you.